And then share screen. All right. Are we back?
Yes.
Okay, I hope it works now. If this does not work, if it breaks off again, I will just record it here locally and post it later, because I don't think that it's a system here with the internet. It's Zoom that is overloaded. Okay. All right, so coming back to our chapter today, we were talking about the nucleophilic aromatic substitution. And we said that it's complementary to the electrophilic aromatic substitution, but it works very, very similar. So if you think about this, you have an aromatic ring. And usually in order to do a nucleophilic aromatic substitution, you have to have an electron withdrawing substituent X on there. So just as a quick reminder, X is usually something like a fluoride, or less often you see chlorides. So anytime you see an aromatic ring that has a fluoride on there, your alarm bells should ring. That's probably what I'm asking for is a nucleophilic aromatic substitution. Now, so how does this work? Well, we can take our nucleophile here, and we have our lone pair, and we can do the same thing as we did with the electrophilic aromatic substitution, with the only difference now that the nucleophile is attacking the pi system. So we push the electrons into the lowest unoccupied molecular orbital. So we push the electrons in here, and then we can remove the electrons from the pi bond formally out to that position. Now from that, we can draw our resonance structures again. So if we just start with that, so 1, 2, and then we're gonna have a negative charge over here, and we have a nucleophile, and we have our X group over here. And from here we can, as previously for the electrophilic aromatic substitution, we can start drawing resonance structures. So let's say we move these electrons in here and move these out here. Then we're going to end up with a negative charge here, nucleophile, and our X group. And then if we move over one more, you can imagine that you can push the electrons over here and these electrons in here. And then you end up with the last resonance structure that has a negative charge up here. So this is very similar to the concept that we had with the electrophilic aromatic substitution. In fact, it's virtually identical. So this resonance stabilizes this intermediate. And analogous to the electrophilic aromatic substitution, this intermediate state, this charged intermediate state, has a name, and we usually call this in chemistry the Meitner-Heimer complex. Right. Now, what happens at the end? Well, we can push the electrons from this position in, and we can kick the leaving group, this X, out, and that re-aromatizes the system, so stabilizes the system overall again. And what we did formally is essentially an ipso substitution of the X group, so that was a chloride or a fluoride, with our nucleophile. All right, so the fact that you need a good leaving group that is very electron withdrawing and stabilizes this negative charge here, so you end up with X minus here essentially, restricts these reactions significantly to reactions where you have either a chloride or a fluoride. But the complex itself is oftentimes, so if you just have a simple benzene ring, it's not easy enough to do this reaction. You usually need additional assisting substituents on there. So most often these are strongly electron withdrawing groups, like for example, a nitro group. So if you go in here, and let's pick an example now, this time, let's say we fluoride. Guys, can you please mute yourself? Okay, so you can unmute yourself if you want to ask a question, but while we go through the lecture, please try to mute yourself. Otherwise, I have your background noise in my ears. Okay, all right. So we need a nitro group or an electron withdrawing group generally to do this reaction. So in this case, let's put a nitro group here in this position, and let's draw our aromatic ring. And for this specific example, let's pick, let's say, an alcoholate. So let's pick methoxide, for example, as our nucleophile. Now, following this mechanism, you'll quickly see why this electron withdrawing group is helping, or is required essentially for this to work properly. If we attack here and we push the electrons out to this position, you immediately see when you draw the resonance structures that you have the negative charge stabilized now directly next to the electron withdrawing group. So let's draw it like this, negative here. And we have the fluoride here, and let's say OMe over there. And these are the two other bonds. So from here on, we can easily draw all the possible resonance structures as we have done previously. OMe. We would push these electrons in here and these down to the para position. So you end up with a negative charge here. And then we can do this one last time. Yeah, so there is one more resonance structure that you can consider here, and maybe I draw it down here because that makes a little bit more sense. Here you could have also stabilized the negative charge on this carbon atom by basically absorbing it into the nitro group. So you can draw an additional resonance structure where you now draw a double bond to this nitrogen, and then you're left with the negative charges on the oxygen. That's basically just the electron withdrawing character of the nitro group drawn as a resonance structure. And this resonance structure is strongly stabilizing and allows this reaction to proceed significantly faster than if you just have a simple unsubstituted system as the one you see up here. Now, the product of this, of course, let's maybe draw it out like this, is again, our substitution of the fluoride plus F minus over here, right? Okay, so I'll give you a couple of seconds to stop the video here to make notes, and then we'll move over to the next slide. All right. So As for the electrophilic aromatic substitution, the attack of the nucleophile is the rate determining step for this reaction. And most of the time we consider these reactions irreversible. So rate determining step is the addition of the nucleophile. So, and if we were to draw out an energy diagram, the same way we have done this for the electrophilic aromatic substitution, where this is your reaction coordinate, and this is an arbitrary energy for our purpose here, a delta E, then we can start out, let's say, we have our starting materials over here. So this is like, let's say, our fluoro nitrobenzene plus our nucleophile. Then the rate determining step is the step that leads to the formation of the intermediate Meisenheimer complex. So this is the highest barrier here. So over here you have all the possible resonance structures. I'm just going to draw one now. So nucleophile, NO2, and let's put the negative charge over here. And from there on, it usually goes down in energy towards the products, where you then have OMe, NO2, plus, in this case, F minus. So this is a lower barrier, and it goes down, down here. So the rate determining step is, this is the rate determining transition state here. And this is associated with the attack of the nucleophile onto the aromatic ring. So formally, it looks very, very similar to the scenario that we had for the electrophilic aromatic substitution. The only distinction here is that it basically gives you an intermediate with a negative charge, and the nucleophile is basically your attacking group, and the electrophile is essentially the empty pi orbital of the aromatic ring. Now, generally speaking, the nucleophile does not actually have to be a charged species. So you can do the same reaction with neutral species. So let's move this over here. So nucleophile does not have to be charged. So it can be a neutral species. And just to give you an example here, if we pick something like this, and again, we're going to have an electron withdrawing nitro group in that position. And just for the sake of this example, we're going to pick a chloride here. You can easily attack this with a secondary amine. Let's just pick something cyclic here to make it more interesting. Under fairly mild reaction conditions, so you can do this in water, and you have to heat it a little bit. Let's say about 100 degrees Celsius or something like that. You can get to the intermediate. So again, this first step here, the attack of the nucleophile, is the rate determining step. So let's do this like this, negative charge over here, and then chloride. And there's a positive charge now here. So it's a lone pair on the nitrogen that attack the system. And you can draw all the resonance structures. I'm not going to do this here. But ultimately, that can give you then the substitution product. So it's a form, a clever way of doing a direct amination on an aromatic ring. It's not the most modern chemistry. Most people today use cross-coupling chemistry that we're going to talk about after the spring break. So transition metal catalyzed reactions. We're going to get to those at a later stage. But this is kind of like a very elegant way if you have a system that has an electron withdrawing group attached to this. So just as a practice, I suggest that you can draw the mechanism out for this reaction. And draw all the intermediate resonance structures that you expect for this reaction. There's actually plus, what do we have? HCl as a side product, right? Draw mechanism. All right, so there are a couple of characteristics that are very, very important for these reactions in order to work well. So characteristics of good SNAR reactions. And we're going to list them down here. So one is the one that we already addressed today, and that's that it needs a strong electron withdrawing group, ortho or para to the leaving group. So point one, strong electron withdrawing group, usually ortho or para to the leaving group. And remember, the leaving group X is usually
Professor?
something. Yeah?
Oh, the screen is frozen.
Why does it not update? Let me quickly stop share and see if I can fix it. Okay, I think it should be working again. Yeah, okay. All right, so what I said is that the characteristics of a good SNAR reaction requires a strong electron withdrawing group, ortho and para with respect to the leaving group. And remember, the leaving group was this X group that we defined at either as a fluoride or as a chloride. The second point that we want to bring up is that the more electron withdrawing groups you have on the ring. So if you don't just have one nitro group, let's say you have two nitro groups or a nitro group in a nitrile or something like that. So the more of these groups you have, the faster the reaction will proceed. So the more electron withdrawing groups, the faster the reaction. So a classical example that you'll see is something like this. This is actually a reagent that has been used in sequencing because nucleophiles can substitute this position here, and the resulting product is a very fluorescent dye that can easily be detected with spectrometers. Now this, for example, because it has two electron withdrawing groups, reacts significantly faster than the analog that basically just has one electron withdrawing group. So we had, for example, a nitro group in the ortho position, and that's more or less the same as if you have the nitro group in the para position. So overall, the reactivity of these two is more or less the same. Now, of course, the leaving group itself has an important influence on that. And we mentioned already the most common ones that you'll see here are fluorides or chlorides. So 0.3, so electronegative leaving group. So if you compare directly the fluoride and the nitro group, sorry, the fluoride and the chloride, the fluoride is about 300 times faster in reacting than the chloride. And that's significant, right? So that is a significant lowering of the barrier. And you can explain this simply by making this position here next to the fluoride more of an electrophile. Because of the electron withdrawing character, there is basically a much more polarized, positively polarized carbon atom next to this fluorine than next to this chlorine. So reacts 300 times faster than chloride. Something that you might not immediately have expected, but it's a very common substrate for these nucleophilic aromatic substitutions are heterocycles, in particular those heterocycles that are electron poor. So very common substrate. Electron, let's say, deficient heterocycles. So one typical example that you'll see often in the literature are substrates that are derived from pyridine. And usually those are made directly from pyridones. So that's a commercially available amide. And if you treat this, so pyridone, and if you treat this with a chlorinating agent like POCl3, and you can work out the mechanism how this works, like it's the attack of the oxygen on the phosphorus, etc. We've done this a couple of times already. You can turn this into the pyridine. So that's the aromatic system that now has a chloride in this position. It's essentially the same activation that we had as part of the Vilsmeier-Hack formulation, right? Just now that the amide is part of a ring system. And if you treat this now with a nucleophile, you can easily substitute this chloride here and incorporate the nucleophile into the aromatic ring. So that's a very common reactivity that you see with pyridines. So nucleophile plus CO minus here. Now, the reason that this works quite nicely, you can think about it this way, is that if you were to draw the resonance structures out for this, you can place the negative charge directly on the nitrogen atom, the most electronegative element in the ring system. And you have the leaving group here and the nucleophile right next to it, right? So you can draw all the other resonance structures for that. But this is the most important one that basically places the negative charge on the electronegative atom. So places negative charge on an atom. And that stabilizes the system, of course, more so than if you place it on a carbon atom, for example. All right, now let's talk a little bit about the relative rates of these, just to give you an idea of how much more reactive these heterocycles are in comparison to unsubstituted benzenes. I just want to give you kind of a little bit of a scale here. So relative rates. So let's take our standard here and let's take this as a reference. Let's just do chlorobenzene as a reference. And we're gonna put the rate here. And this is just a relative rate with respect to chlorobenzene. And let's say that this is 1, we define this as 1. Now, if we place a nitro group right next to the chlorine, the rate of this reaction shoots up massively. So this is 7 times 10 to the 10 with respect to the unsubstituted one. So this is a massive increase in reactivity. And that's why I said, like, anytime you see something like this, a nitro group on an aromatic ring and something like a leaving group, a chloride or a fluoride, your alarm bells should ring that this is probably going to be a nucleophilic aromatic substitution, right? Now the pyridines are somewhere in between that, but still are closer to these activated systems. So if I have something like this, for example, this is about 3 times 10 to the 8. So it's about 100 times slower than the nitrobenzene here. If you have it in the para position, then it's comparable still. So chloride, nitrogen here, that is about same range. This is 7 times 10 to the 9. And there is a significant difference then when you come down to the meta substitution in pyridines. So if you have the chlorine here, this is significantly less reactive than these two substitution patterns. This is only about 9 times 10 to the 4 times faster. Now you can think about this as a substituent effect, because in this case, in these two cases, you can localize the negative charge in one of the resonance structures on the nitrogen. So let's say negative charge stabilized by N atom. And if you were to draw the resonance structures for this system here, you can't draw a resonance structure where the negative charge comes to rest on the nitrogen. So that's why the stabilization of the Meisenheimer complex in this case is weaker than in this case. So we can say like weaker stabilization in intermediate. Now, of course, you can push this this even more if you think about that. If you make the aromatic ring even more electron poor, so let's call this just more nitrogens. So if you go to other heterocycles and you incorporate more pyridinic nitrogens into the system, like let's say you have a system like this one that now has 2 nitrogens at these positions, and in between that you have a chloride, then this is of course more reactive than the one where you basically just have 1 nitrogen. And the reason is simply that you now can draw 2 resonance structures that place the negative charge on a nitrogen atom. So think about it this way. If you have something like this, you can draw resonance structures. Let's say chloride, and we pick our nucleophile here. The first one, we're going to put the negative charge here. And then we can draw all the other resonance structures for the system. that's wrong, sorry. We move this one over, then the negative charge ends up here. And we have something like this. Cl, nucleophile. And then the last one, so let's draw this out this way. And then this way, and move it over to the nitrogen. So now you basically have two resonance structures, this one here and this one here, that basically places the negative charge on the most electronegative atom in the rings, on the nitrogen atoms. And this is double the stabilization essentially that you would expect to get from a simple pyridinic nitrogen atom in a ring. Now, the last thing that you should maybe remember here is that all of this applies to electron-poor aromatic rings. So electron-rich aromatic or heteroaromatic rings are unreactive in this nucleophilic aromatic substitution. So electron-rich heterocycles are unreactive. So you get no SNAR with, for example, pyrroles, let's say furans and thiophene. Right? So don't expect these to undergo the nucleophilic aromatic substitution. You really need the electron withdrawing character here. All right, so with that, I want to shift to the last part. It's a relatively short section of this chapter 23, and it's the last part that we need to cover before the midterm, and this are benzyne substitution mechanisms. So benzyne substitution is a similar mechanism that, well, it looks at first glance a little bit similar to the ipso substitution that we had talked about previously, where we substituted a T-butyl group or a TMS group, but it works a little bit differently. So bear with me for just a second. So 10b, this is benzyne substitution mechanism. Now this is the last way essentially that we're going to discuss of how to do substitutions on aromatic rings. And it was first discovered by Roberts in early 1950s. So it's quite old chemistry actually. And the substrates that were under investigation where this was discovered is basically simple aromatic rings that have like an electron withdrawing substituents like chloride here, for example, and hydrogen next to it. And what they found at the time is that when they treated this reaction with a very strong base, so sodium amide, in liquid nitrogen, liquid ammonia, sorry, NH3. So this is liquid ammonia. What they got is essentially the amination product. So they got as a product out this here, right? And at first glance, you might think like, well, this is just a nucleophilic aromatic substitution, just exactly the same way that we have talked about just a couple minutes ago, where basically this amide NH2 minus will act as the nucleophile and displace the chloride. Well, at first glance, it appears to be like that, but we know already that this is not an a viable substrate for a nucleophilic aromatic substitution. So it's not a good substrate, SNAR substrate. It just reacts far too slow. So the next experiment that they did is essentially they took C13 labeling and they basically placed a C13 label. So that's 13C carbon atom at this position and just followed this through the reaction. And just to make sure, they wanted to figure out whether the nitrogen of this amide actually attacks at this position or if it basically scrambles around the entire ring. And the curious thing that they found is that they got a mixture of products where 50% of the time the C13 label was in this position, and 50% of the time it shifted by one position over. So you got something like NH2 like this, right? And it was perfect 1-to-1 or 50% to 50%. And that's kind of a giveaway already at what is happening here a little bit, that this cannot be just a simple SNAR substitution as we have talked about before. So let's talk about the mechanism of this system that explains this, this selectivity. So again, if we take our substrate and we use the very strong base, so the sodium amide, H2N. What this is going to do is it's strong enough that it can deprotonate. I'm going to keep the label here for the C13. It can deprotonate the aromatic ring. So this can abstract a proton here, and that can push in the electrons over here. And we talk about what it forms in just a second, and kick out the chloride as a leaving group. So think about this as just a simple elimination from the conjugate base. So that then gives you something that you probably haven't seen before. And it takes a little bit of getting used to accepting this. But the way we usually draw this then is with a triple bond here. So this is basically a double bond here, and over here you have a triple bond-like system. It's not a full triple bond, and we'll talk about this in just a second, but it's double bond-like. So another way to draw this structure, what you often see in the literature, is as a diradical. So where you basically draw this out like this, and then you can basically draw...
Hi, Professor.
Yes?
Sorry, I think the screen is frozen again.
Okay, let me fix this real quick. All right, can you see it now again? I think it works again. It's still recording. Yeah, it's still recording. Okay, so we're talking about this triple bond over here, right? One of them is labeled with a C13 and the other one is a simple C12 atom. Now, you can write this also as kind of a diradical, where basically the lobes of the trigonal planar carbon atom are kind of carrying this radical. And if you think about this in a perspective, if we were to draw this as a six-membered ring in the plane, you have your p orbitals, and then you would have the lobes that carry the electrons basically as sp2 hybridized systems. So this is sp2 orbital that basically forms this benzene type electronic structure here. And now this triple bond here now can be attacked by another equivalent of the amide, the base. So NH2 minus can now attack here. We can push the electrons out here. So this then gives us a negative charge on this position. And I think it's obvious to see for all of you that as long as this is symmetric here, the amide has no reason to attack only here, but it could also attack here. It can't distinguish between these two positions. So the two products that you're going to be forming here is going to be the two precursors for the products that we see up here. So the other one then would be NH2 with a negative charge over here. And just to get this, see if we can get this right here. So this would lead essentially to this product here. And this one would lead to this product by just abstracting a hydrogen from the ammonia. So the ammonia acts here then as the acid, right? And that gives us essentially the substitution product that we see over here. So this is a little bit of an unusual mechanism, and it takes a little bit to get used to that, but it's very well studied based on these isotopic labeling experiments where you basically follow the position of the C13. So if you're faced with one of these reactions, you always have to expect that the substitution will not only happen at the position of the chloride, where the chloride was initially, but it can also lead to the substitution pattern that places the substituent in the position next to it. Because we go through a symmetric intermediate like this one, that you can only distinguish if you use isotopic labeling at these two positions, right? But the chemistry of these is going to be, these two positions is going to be identical. Now, these benzynes are a little bit unusual structurally. Usually if you think about like a triple bond, you don't usually think about this as acting as an electrophile. So benzyne characteristics. So the first thing, if you think about this, the fact that this thing is very strained. So if we draw it as a triple bond within this ring system, it would like to be 180 degrees around this bond, but it's confined in this 6-membered ring. So it's a highly strained, highly activated triple bond. And it also, in some reaction conditions, can react in the form, or more characteristically, as a diradical. And we'll come back to this towards the end of Chem 12b, when we talk about cycloaddition reactions and pericyclic reactions. We'll stumble over these benzynes and their reactivity again because of both of these characters, being a very, very activated triple bond and having the potential to react themselves as a radical. Now, the way you can recognize these is that they always form two isomers. Two isomeric products. Because these two positions here are indistinguishable at the benzyne stage. Oftentimes you need forcing conditions. And that goes along with having like a highly strained, highly activated species. So you have to go up in energy when you want to go to the alkyne. And if you look at the reaction conditions, you often see that they use very strong bases. So if you just look at a classical example that should immediately raise your suspicion that you're dealing with a benzyne reaction is if you, for example, had something like this and you treated this with concentrated sodium hydroxide at very high temperatures, so 300 degrees Celsius is something like that, for 24 hours. And the reaction products that you can isolate from that are something like this. Sorry, OH and methyl group down here. And specifically, if this is close to a 50-50 ratio, you can bet on that the mechanism for this reaction is based on some benzyne intermediate chemistry, right? Okay, so the last thing that I want to talk about today is other ways to generate benzynes. All these reaction conditions here, for example, liquid ammonia and sodium amide or sodium hydroxide at 300 degrees, are really brute force methods to generate benzynes in reaction conditions. And oftentimes, the reagent that you want to introduce at this stage is not stable under these reaction conditions. So practically, there have been many other ways that have been developed to generate a high energy intermediate benzyne in a reaction. And I just want to go through a couple of examples that illustrate this. And they are also very, very characteristic of benzyne chemistry. So anytime you see something like that, your alarms should go off, right? So other methods to generate benzynes. So let's say A here. The first one is based on essentially a Grignard reaction. So anytime you have an aromatic ring and you have a good leaving group, so oftentimes this is a fluoride or a chloride, and you have another halide here, let's say a bromide, you can form essentially a Grignard reagent the same way you would do it with any other aryl or alkyl halide. So magnesium 0 and let's say THF. And you heat this a little bit. And what you generate as an intermediate is the Grignard reagent of this mixture. So you have the fluoride here, and then you have magnesium Br. So that's your Grignard reagent, right? And you can quickly see here that this is essentially already set up for the elimination. You have your leaving group here that you can kick out as fluoride, and the electrons from this metal organic bond here, this carbon magnesium bond, can be pushed in here and generate your benzyne, right? So usually this is called the halo elimination reaction. So if we draw this out, and just to make it a little bit clearer, I'm going to push the electrons around, plus then magnesium BrF is the salt that you're generating. And this is how here your benzyne intermediate. Of course, you can't isolate this. This will immediately continue to react, but you generate it essentially in situ. Now, another way to do this that avoids organometallic reagents is to use the cleavage of silyl groups. And we've seen this previously that TMS groups, for example, are very good leaving groups if you treat it with fluoride. So let's see, let's put a really good leaving group on here. So CF3. And then we have here trimethylsilyl group, right? So this triflate up here is a good leaving group, the same way that the fluoride was a good leaving group. And the way we basically get rid of this trimethylsilyl group is the standard way that we cleave silyl groups, and this is usually with fluoride, some form of fluoride source, so F-. This could, for example, be cesium fluoride or tetrabutyl ammonium fluoride. We've seen this before, TBAF. And that will basically give you an intermediate where the fluoride has attacked the silicon. I'm going to abbreviate this here as the triflate OTF. And then you have silicon, and it has fluorine on there now, and still Me3. Of course, this is now a negative charge here. And from here on, you can basically draw the arrows again. This kicks out as a leaving group, and this goes in here. And you again generate a benzyne plus Se Me3F. Okay, so the last one is something that we've seen similarly before. It's a combination essentially of a Sandmeyer reaction and a decarboxylation. And that's the last one, last way to generate a benzyne that we're going to talk about. So if you have something like this, antranilic acid, OH, and you have an amine here, you can treat this with sodium nitrite. And you need an acid like HX, for example, in here. And what this is going to generate is the diazonium salt of this. So we're going to get basically NN plus here, the same way we did this in the Sandmeyer reaction. So OH, and then N with a positive charge now here. And you have like this X minus counter ion floating around. And from here again, we know that this nitrogen is a fantastic leaving group, and we can cleave this part here essentially as CO2. So pushing the electrons in from here cleaves like a proton. Then we can push these electrons into the triple bond, and we can take these electrons and push them out towards the nitrogen. And that then gives us another way to form an arine or a benzyne, right? Plus N2 that escapes the reaction mixture plus CO2. And both of these basically can be removed from the reaction mixture. So all of these are ways to generate benzynes from relatively simple, easily accessible precursors. And these are just kind of some of the tricks, or that's actually most of the tricks that are known in the literature to form benzynes under controlled reaction conditions that do not require like excessive temperatures like 300 or 200 degrees or liquid ammonia or something like that. Okay, so this is all I wanted to cover today. As part of this lecture. I will keep you updated how we're going to solve the problem with printed copies of the exam. I'll sort this out with the GSIs today, and I'll send an email around later today where you can pick them up and where you can drop them off. So we can collect these on Thursday. Again, I will definitely post the exam at 8 a.m. Online, and we'll figure out how to give you access to printed copies if you're still on campus and you don't have access to a printer. Okay. If there's any more questions, please come to my office hours. They are just right after this in about 15 minutes. And I can answer more questions there in a little bit smaller round. Okay, so I hope there was everything. I'll keep you updated via email on B-Courses. If there's any more questions, just shoot me an email or come to my office hours. Okay, all right, see you guys.
Thank you.